Integrals, area, and volume well explained. In school, you learned area is a two-dimensional measurement found with the formula area equals length times width. This formula can be visualized with a length segment transported along a different dimension or a perpendicular dimension, and an area is created by leaving many segments behind it. This is the general idea of an integral. An area is just segment lengths all lined up in a row. The segments are integral to the area. In calculus, when we're talking about area, we're talking about the original length of the figure as the function of an input that is the width. And of course, in calculus, the width can change to different values. As the width changes to different values, the length might change. In this case of a rectangle, it doesn't. The green line is the function f of x equals 5. So it is a constant linear function. I'm going to show you an area in terms of integration. So the length of this area we're about to create is the function value. In this case, it's 5 the whole time. The width is the input value. As I change the input value to 1, to 2, you can see that you can visualize the integration as all these segments being left behind and lining up, and we're basically creating an area by lining up all of these segments. That is an integration. The area of this figure is an integration of these infinite segments that are created between as I change from 0 to 4 on the input value. Since all of the output values are 5, no matter what the value of x is, you can see we create a simple rectangle. In terms of integration notation, you just witnessed the integration of f of x equals 5 over an integral of 0 to 4. So the integral is the area created. As the input value changes, that's what dx means, as this input changes from 0 to 4. And of course, you know that that integral will equal 20. Now, of course, dealing with integrals, you won't be given an easy function like f of x equals 5. You'll be giving f of x equals something with an input value. In this case, let's step to the next easiest function, f of x equals x. And of course, as the input value changes, we call this the dx. The output value is going to get larger and larger. Of course, it's equal to the input, because that's the nature of this function. And we see a triangle being formed, a perfect isosceles triangle here. And that is the integration of the function x over an interval of 0 to 5, right? Remember what integration is. It's just adding up all these segments together. It's like as if they have a width worth of lengths. There they are. These segments create an area. Now, what if we have a funky function here? This is a 0.5x plus sine of x. It still works the same exact value. The input value is like the width of the area, and the output value is that funky length. So the length is forever changing depending on the input value, of course. But that is still an integral, and you still can figure out an area. That's the wonder of integrals, is you could find these areas with some very, different function patterns that you normally wouldn't with normal 10th grade geometry. Now, of course, by now you should have realized you can estimate these areas by creating rectangles that have a width of the input and a length of the output, as we discussed prior, and adding up the areas of these rectangles. We know this as the Riemann sum. And you could think of integration as the perfection of the Riemann sum. That's what it is. All right, so you could think of a curve made up of many rectangles. The integration, or the integral, is the area of all those rectangles added up. And the smaller the rectangles get approaching a segment, the integration perfectly adds up all those tiny, tiny areas to give you an area under the curve to the x-axis. That's what integration is. All right, so now we know area is this made up of segments or very tiny rectangles, all the areas added up together. That's what integration is. Think of volume as the same exact concept, except you're now, instead of moving a segment along a perpendicular dimension, you're going to be moving a whole area along a perpendicular dimension, just like as follows. Watch that rectangle there, and we're going to move that rectangle in another dimension. So we have this rectangle here. Started out as a rectangle. We'll call it a base angle, or excuse me, a base polygon. And you'll see that a whole bunch of areas stacked up create what we know as volume, a three-dimensional volume. We're going to be using the same concept here when we're talking about using integrals to find volume. Now, in terms of the graph, imagine this red axis right here is the x-axis. And the y-axis, in terms of functions that we know about right now, or two-dimensional xy axis, is the blue. And we're going to be talking about integrating these areas that are created as my x input changes. Watch. So, as I change along the x input, it's going to create a volume. In this case, it's a cylinder, because the base shape here is a circle. Now let's talk about exactly what's going on and how the x-axis and the y-axis and everything is related to the area of a circle and the volume right now. So here's the cylinder we created by dragging an input variable up the x-axis. For our sake, I'm going to hide all of these areas so we only see the starting area here and the ending area here. In other words, the two bases of the cylinder. And we change the height by dragging along the x-axis. Okay? So for our purposes, the height of the cylinder is the change along the x. That's the dx, is the height of that cylinder right there, right? And the radius of the cylinder is the resulting value along the y, or the f of x. So as we're changing the x here, was the radius changing at all in our case? No, not for this perfect cylinder. The radius stayed the same the whole time. Just like the rectangle at the beginning of the video. Therefore, there's a constant function here determining the radius of this circle, and therefore determining the radius of the cylinder that's created. So the dx is that factor along the x-axis, the change in the input value. And the volume happens when we integrate all those areas together, like that. That's where the integration occurs. We're integrating all of these areas into a volume. Now, what if I were to have our simple function here, f of x equals x, with this being the x-axis and this being the y-axis, right? And we have our good old diagonal function, f of x equals x. Now, what if I were to create circles in this example, with the center of the circles being the x-axis and the radius being the function itself, the length of the radius being the value of the function, dependent on the x. So here I'm on the x-axis, and I'm going to create a circle that has a radius of the function. And what if I were to create a bunch of these circles? As you see, as I go farther down the x-axis, the circles I'm creating are going to be larger because this function is getting larger. We call these circles the base areas that we're using for this particular volume. And you can see what's happening here. As I go along the x-axis, I'm creating larger and larger circles. Here's what it looks like in 3 dimensions. It's as if we're creating a bunch of circles lined up, and the radius is dependent upon the value of the function itself. There we go. Now, it's important to remember how, with the 2-dimensional just xy, we estimated the integral by finding the area of all these rectangles in a Riemann sum. The black outlines, of course, the actual integral, whereas the rectangles are the estimate. Volume works the exact same way. We're going to use the integral to find the exact volume of this solid created by changing the input x, by pretending each of these exact points along the x can create cylinders that we're all going to add up. Of course, the integral of these circles is going to be the perfect volume measurement. These cylinders show an estimation. And here is the integral of each of those circles as the input changes. And as you can see, the integral of circle areas where the radius follows a function f of x equals x creates a cone. And the radius of the base circle we used moving along the x-axis here, the red line, is the value of the function. As the value for x changes, we know it as dx, the radius changes as well, creating larger and larger circles, which integrate to create a cone. So the logic behind it is the change in the input value known as dx, which in an area is considered to be the width, results in change in the output function, f of x, the curve on the graph, and we'll consider that the length of the area. We know from geometry area is basically length times width. In calculus, the changing area is the changing width times the length with changes as a result of that changing width. Putting these together, we have f of x dx. The integral of that is the area underneath that curve of f of x as the input changes. Integral designates the interval of the inputs. In this case, it's 0 to 5. As the input changes from 0 to 5, what is the area created? Sometimes we introduce a base area. This is different than the area underneath the curve. This is a specific shape. In our examples, we were looking at a circle as the base area. And in our case, we made the radius of that base area the function itself. Therefore, as the radius changes, so does the volume as these individual circles are integrated. And the areas of these individual circles change depending on d of x. the change of the input. Therefore, volume is the integration of all of those changing areas. Now, of course, that's the general idea. F of x is not always going to be some nice little f of x equals x straight line. It could be something funky, you know. So you'll have to find the volume as these circles change, as the radius changes following that funky function. But it's all good though, because with your techniques of integration, you could find the volume of this crazy looking shape based upon the idea that you're going to add up all those little cylinders that are created. And that is the basic idea of integration involving area and volume. Pay attention for my next video coming up with different base shapes. Sometimes a base shape could be a semicircle instead of a circle. Sometimes it could be a rectangular prism. Sometimes it could be a triangular prism. But this is the basic idea of volume with integration.